Another way to make alcohols is via the use of reducing agents, and we saw reducing agents when we explored additions to alkenes in first semester organic chemistry. If you remember, hydrogen with a certain transition metal, either platinum, palladium, or nickel, one of these, not all three, will add hydrogen to each side of the alkene, giving us the saturated hydrocarbon. We can do the same thing if we have a carbonyl. So we'll do the same thing, the same reagents. In this case, the oxidation state is 2+, and if we reduce our carbonyl, we're going to add a hydrogen to each side of that double bond. So we end up with an OH on the top and a CH on the bottom. And now if we calculate the oxidation state, you should end up with 0. How do we know that? Well, remember that the middle carbon has a single electron from each CC bond. It has both electrons from the hydrogen that we just added, and it lost all the electrons to the oxygen. So it ends up with, in our our oxidation state count, it ends up with 4 electrons. Compare that to 4 valence electrons, and we get the oxidation state of 0. There's another way that we can reduce carbonyls, and that's through the use of sodium borohydride. And the Lewis structure is more properly drawn like this, with 4 BH bonds. We saw this in the addition to alkenes chapter, where we used it to reduce the carbon-mercury bond in the hydroxymercuration reaction. So we have a BH4- and an Na+. And of course, as we've learned, the sodium plays no role in the reaction. We have just the BH4-. And you might think of the BH4- as a source of H-. So this is a source of hydride. And we can use that to reduce carbonyls. So let's look at acetone again. We could use hydrogen and platinum if we wanted to, but maybe we didn't have any of that available in our laboratory, or we're looking for something that doesn't require high pressures or potentially unsafe conditions. NaBH4 is a white powder that's easily obtained from the chemical company. It is not unstable, it is not highly reactive. It will sit in the jar as a white powder for quite some time. Remember that the carbonyl has a dipole moment, and so any nucleophile should add to this central carbon right here, and that will be a feature when we get to the aldehyde and ketone chapter. But right now, if we have BH4, we essentially have 4 equivalents of H-. We can use one of those as a nucleophile to add to our carbonyl. And so this is a nucleophilic attack, arrow push pattern. And here we end up with the alkoxide intermediate. Here's the newly formed H, and we have BH3 as a byproduct. It turns out we could do 3 more of these with this same boron reagent. So this boron reagent could reduce 4 ketones for every BH4- that we start off with. And in this case then, we're going to take the proton source from the ethanol, and we're going to protonate the alkoxide, and that gets us to our product, which is the same product I drew using H2, isopropanol, but in this case, you see we have a nice simple 2-step mechanism, nucleophilic attack, followed by proton transfer. So that is a reduction using sodium borohydride, and that's a very common way of reducing aldehydes and ketones. So let's make a note here. This works for aldehydes and ketones. If we need to reduce, say, carboxylic acids, amides, or esters, we have to use something else, and we'll talk about that on the next page. So lithium aluminum hydride is also a source of H-. And in this case, the lithium plays no role, and we have 4 aluminum hydrogen bonds. This one's much stronger. My TA, when I was in your position, talked about this being the atomic bomb of reducing agents. It will reduce anything and everything. It does react with protic solvents. If you noticed on the previous slide, the sodium borohydride reacted in the presence of ethanol with no problem. It did not react with the proton on the ethanol molecule. If I were to mix lithium aluminum hydride with ethanol, I would have probably a small fire or explosion, because the H- would react very quickly with the hydrogen on the ethanol, making H2 gas and giving off lots of heat, and that has the potential to ignite the H2 gas. So in lithium aluminum hydride reactions, we need to specify two steps. The first step is addition of lithium aluminum hydride. Sometimes we abbreviate this with LAH, and I'm okay if you do that. So we can reduce our writing by just using LAH. The second step is then addition of a protic solvent, sometimes water, maybe an alcohol, and we end up with what you'd expect, the reduced ketone. As I said, this is a stronger reagent, and so we can take, say, a carboxylic acid, which would not react with sodium borohydride, and we can react it with lithium aluminum hydride, follow it up with water, and essentially we're going to add two hydrogens to this position here, and we're going to end up with the primary alcohol. And this will also reduce esters. And it's important to note that the same reaction with NaBH4, and actually this is a multi-step reaction, so I'm going to get rid of that one, gives us no reaction. NaBH4 will not react with carboxylic acids. Lithium aluminum hydride will. And it will also react with esters. So let's look at the ester reduction using lithium aluminum hydride. Here's a simple ester. And again, we're going to have our multi-step addition with lithium aluminum hydride followed by water. The first step is aluminum hydride reacting with the ester. Just like with a ketone, we have some dipole moment here, and we can receive the electrons from the nucleophile, which is again the H-. So we're going to get this intermediate. And now we have what we call a tetrahedral intermediate. Because we've formed a tetrahedral carbon in the middle here. That can collapse, losing the somewhat good leaving group. In this case, because we're in strongly basic conditions, basic coming from the H- source, we can lose the OCH3- as a leaving group. This is loss of leaving group. This was nucleophilic attack here. What we form is an aldehyde plus methoxide. Now the aldehyde is more reactive towards a reducing agent than is the ester. So now we've formed an intermediate that's more reactive than the ester. It's going to immediately react with another equivalent of lithium aluminum hydride, and I'm just going to draw the H- here. And of course that H- can act as a nucleophile just like it did with an ester. And now I've added a second H. I now have, this is ethanol or ethoxide. Hopefully you recognize that. And the second step, addition of water or maybe a mild acid, we could protonate the ethoxide to make a primary alcohol. And so you see that the ester, which had a carbon chain here, and I could put an R here if I wanted to and just modify all of these drawings. So I can do this with any ester, of course, and that will get me any shape of primary alcohol. We're still going to get a primary alcohol from this ester because the carbon that's right here, and I'll try to highlight that in red here, this carbon will receive two hydrides. One will kick off the OCH3, the other will reduce the pi bond to a single CO bond. We will always end up with a primary alcohol whenever we reduce a carboxylic acid or an alcohol. And you should be able to go through here and prove to me that the oxidation state has changed. So let's look at the ester oxidation state. If we take this carbon here and give it half the electrons from the carbon-carbon bond on the left, give it no electrons from any of the O's, we see that we have a +3 oxidation state to start with. And if we look at that same carbon in our product, we give it half the electrons from the carbon-carbon bond, 2 electrons from one of the hydrogens, 2 electrons from the other hydrogen. Now it has 5. We've gone to a -1 oxidation state. And you can see that we've decreased our oxidation state by 4. Each hydride results in a decrease of the oxidation state number by 2 units. And so we've essentially lost, we've done a double reduction in this case. So some practice. What is the product here in this case? When doing a reduction, all we have to do is take this central carbon and add a hydrogen to it. In this case, there is only one hydrogen to be added. We end up with a primary alcohol. If we had something that looked like this, we could do the same thing, NaBH4. Now, of course, in these cases, lithium aluminum hydride would work too. It's just that it's more reactive than we need. The sodium borohydride will work just fine. We don't have to use the expensive, dangerous lithium aluminum hydride to reduce these aldehydes and ketones. And now we see that this carbon has gained 1 hydrogen in its reduction. One last example. What if we wanted to reduce this ester and we had a carbonyl here? If we used lithium aluminum hydride, we would actually reduce both of them. There's no way to prevent the carbonyl, the ketone, from being reduced. The ester would get reduced. And so we'd end up with the secondary alcohol from the ketone, and we'd have a primary alcohol from the ester. So everything would get reduced, in this case, in the presence of lithium aluminum hydride.